Hello everyone. In today's lesson, we're going to be looking at limits of sequences. So to begin with, first we're going to define what a sequence is. So a sequence is just an ordered list of numbers, A1, A2, so on and so forth, going on forever. So basically it's going to be an ordered list of numbers that has some way that it grows or shrinks or does something or cycles. And we're going to be looking at how would we determine what's going to happen, its behavior as it goes on. So what would happen in terms of a sequence as n grows? So let's say, for example, that we have an equals 1 over n. So the first thing we're going to do is we're going to just plug some numbers in. So if I plug 1 into this, I'm going to get 1 over 1. So the first value of my sequence is 1. When I plug 2 in, I get 1 over 2. When I plug 3 in, I get 1 over 3. When I plug 4 in, I get 1 over 4. And this is going to continue on. So what's happening as our n grows? Well, in this case, it's shrinking and shrinking and shrinking, and it appears to be that it's approaching 0. What about if we had the sequence bn, which is equal to -1 to the n? So again, let's plug in our values. We plug in 1, we get -1 to the 1 power is going to be -1. If I plug in 2, I get -1 squared, which is going to be +1. If I plug in 3, I get -1 cubed, which is going to be -1. And then basically it's going to continue oscillating between -1 and +1, -1 and +1. So in this case, it does not approach any number. So this sequence will go on forever, going back and forth between -1 and +1. What about if we had the sequence Cn, which is going to be equal to n squared? So let's plug our numbers in. 1 squared is going to be 1. I plug in 2, I get 2 squared. This is going to be equal to 4. I plug in 3, 3 squared is equal to 9. 4 squared is 16, 25. So what's happening with this one is, well, in each step of this, it's growing, but it's starting to grow faster and faster and faster and faster. So basically what's going to happen is our terms are approaching infinity. And this is really kind of what we're looking at, is we're looking at the behavior as we go forward. So as we start at step 1 and we go forward, is it converging on some number? Is it diverging off to infinity? Is it going back and forth and oscillating between two values? And this is the idea behind what we're doing when we take a limit. Let's define what a limit is. A sequence, an, has a limit L if we can get the terms of an arbitrarily close to L by taking n sufficiently large, meaning that basically if we were to look at this sequence and take it and get it bigger and bigger and bigger, the n, not the sequence itself, what happens as with the behavior as we continue this on? So what we're going to do is we're going to write this as the limit as n approaches infinity, and then we're going to apply this to our sequence. And if it approaches some value, this would be the limit. So it's going to be limit as n approaches infinity, an equals L, if the terms of an approach L as n becomes very large. That is to say that our sequence, an, will approach the limit L as n approaches infinity. Now, a sequence is convergent if a limit exists and is a real number. So if it converges to a specific number. So an example of this might be something like, if I have some sequence that appears to be converging to a very specific number, then this would be convergent sequence. A sequence is divergent if no limit exists or the term approaches plus infinity or negative infinity. So this means that, for example, when we were looking at our sequences, when it was going back and forth from -1 to +1, that would be divergent behavior. It does not converge to a specific number. If it goes and grows up to infinity, this would be divergence. If it shrinks down to negative infinity, this would be divergence. So an example might be, let's say we have the limit as n approaches infinity, 1 over n. Well, what's going to happen as we plug in our sequence values? We plug in, this is the first one we looked at. We plugged in, it was 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4. So what's happening as this is growing? Well, it's shrinking in this case, and this one is not going back and forth between -1 and 1. So what's happening is this is approaching 0. right? Because for every term in the sequence that we go up, we're actually getting smaller and smaller and smaller. We're getting closer and closer to zero. So if I were to plug in like a billion, this would be some tiny decimal. If I were to plug in a trillion, if I were to continue to grow my n, this term would get smaller and smaller and smaller, approaching zero. If we had the limit as n approaches infinity for -1 to the nth power, what's going to happen with this one? Well, if I plug in 1, I get -1. If I plug in 2, I get +1. If I plug in 3, I get -1, +1, -1, +1, -1, +1. And it's going to repeat this over and over and over again. So this means that a limit does not exist. What about if I had the limit as n approaches infinity, n squared? Well, what's going to happen with this one? Well, if I plug in 1, I get 1 squared is 1. I plug in 2, 2 squared is 4, 9, 16, 25, 36. It's growing, and it's growing faster and faster and faster with each step. So basically what it's going to do is it's going to go up, up, up until it's approaching infinity, which means this actually diverges. So this first one is an example of a convergent limit. It's converging on a specific number, in this case, 0. The second one diverges. It doesn't have a limit that exists. The third one diverges because it is approaching infinity, which, like we said, if it approaches infinity or negative infinity, this would be a divergence. Here you can see some examples of what this behavior might look like. So our top left graph is a sequence that is converging. So notice it starts up kind of in the top left, and then each term that you go to the right on x, it's getting smaller and smaller and smaller until that y value is approaching 0. The top right is one that is converging on a value. So while this one is going up and then down and up and down, it is oscillating in our y values. It is oscillating around a single point as it gets smaller and smaller and smaller and converges on that single point. So it's converging to some point L. The bottom left shows a graph of what it might look like if it diverges to infinity. Notice that it's getting, as x increases, our y is getting bigger and bigger, faster and faster. And then the bottom right also is a sequence that diverges because it's not changing. It's not approaching some value, but what it's doing is it's going from one value to another, one value to another, back and forth, and it'll continue this cycle forever, never converging on a single value. So now let's define our limit laws. So we have our limit laws, which are that we have, so if our sequence an and bn are convergent sequences, so they're convergent sequences, and c is a constant, then the following rules will be true. The first rule is that if we have the limit as n approaches infinity, an plus or minus bn, so we're saying is if we have the sequence an and we're adding the sequence bn, or an and we're subtracting the sequence bn, this is going to be equal to the limit as n approaches infinity, an plus or minus the limit as n approaches infinity, bn. So remember before I talked about how I'm going to be showing a lot of steps? This is one that I will show a lot. For example, if we have some sequence and added or subtracted and we're taking a limit, a lot of times students will just jump straight in, taking the limit of the first, taking the limit of the second, figuring out what it is. But I'm actually going to break it down into, it's actually the limit of the first, it's the limit of the second, and then you add or subtract them, just to keep our steps consistent. The second law is that if we have the limit as n approaches infinity constant times one of our sequences, this is going to be the same thing as c times the limit as n approaches infinity of our sequence. So pretty much what it means is that if I have a constant times this sequence and I take the limit of it, I can actually pull that constant out, and it's the same thing as taking the limit of the sequence and then multiplying by a constant. So basically what it's kind of saying is that if I had some sequence and I multiplied every term by 2, it would be the same thing as taking the entire sequence and then multiplying that by 2. Our third law is that we have the limit as n approaches infinity on a constant c is going to be equal to c, because what this means is that if I have some constant value and I take the limit of it, it's not changing. So the limit as n approaches infinity will still be c. Or if you wanted to try to use a rule like this, it would pretty much be that you're going to pull your c out and then you're taking the limit of 1, which is just going to be 1. So 1 times c would give you c. Our next rule, rule 4, is that if we have the limit as n approaches infinity, and we have an times the sequence bn, this is going to be the same thing as taking the limit of an as n approaches infinity times the limit as n approaches infinity on bn. Similarly, if we have the limit as n approaches infinity, an divided by bn, this is going to be equal to the limit as n approaches infinity on the sequence an divided by the limit as n approaches infinity on the sequence bn. Now, these actually are technically kind of the same rule, because if you think about it, this division, an divided by bn, would be the same thing as saying an times bn to the -1, in which case this would be, when we do this, it would become the limit of an times the limit of b to the -1, and then in that case, you just, this is actually kind of the same rule. Exponential, multiplication, division are kind of the same. Next rule we have, number 6, is that if we have the limit as n approaches infinity, our sequence an, and this is to the p power, this is the same thing as taking the limit as n approaches infinity, an, the entire thing to the p power. Our 7th rule is going to be that if we have the limit as n approaches infinity, 1 over n to the power p, this will be equal to 0, or it converges to 0, for p greater than 0. And this is because basically what's going to happen is if I plugged in 0 power, this would be 1 over any value n to the 0 power is just going to be 1, so 1 over 1 is going to be equal to 1. If I plug in a negative power, it's going to actually bring it up to the top, which would make it bigger. Any power that's greater than 0 would make the denominator larger, which would then in turn make the entire fraction smaller as it gets smaller and smaller and smaller and approaches 0. Now consider a geometric sequence. So geometric sequence is just a sequence that takes the form bn equals ar to the nth power. So this means that it'll be ar squared, ar cubed, and so on and so forth. So if we take the limit as n approaches infinity of this sequence r to the n, we actually have to consider a few different cases. We have to consider the case when r is between 0 and 1, not inclusive. So in this case, it would be when you have values that are a fraction or a decimal between 0 and 1. In this case, what this is going to be is this is going to be 0 if this is true. If we have that r is equal to 1, then this means that we will get 1, and if our r is greater than 1, this means that it will approach infinity. So what this means is just with our sequence, if we have a power between 0 and 1, then as we take the limit of this, what's going to happen is the power is going to cause it, as the number gets bigger, to shrink. If it's equal to 1, it does not change the value, right? R to the 1 power will always be r. If this power for r is greater than 1, then what's going to happen is that as the limit increases, this power is going to get bigger and bigger and bigger, therefore it's going to get bigger, right? If r is a decimal, then as the power goes up, the value gets smaller. If r is 1, as the power goes up, nothing changes. And if r is greater than 1, the whole thing will get bigger. So if we add the terms of a geometric sequence together, we get an infinite geometric series. That would be S is equal to A plus AR plus AR squared plus AR cubed, so on and so forth. And this would be equal to A divided by 1 minus R. Let's look at a couple examples. Suppose that you have the sequence AN is equal to the square root of n. Then what's going to happen? Well, as I plug in my first term, square root of 1 is going to be 1. Then I'll have the square root of 2, square root of 3, the square root of 4, which is just equal to 2, the square root of 5, the square root of 6, square root of 7, square root of 8, the square root of 9, which is going to be equal to 3, and so on and so forth. So as n increases, what's happening with this? These values are actually getting bigger, right? We're going from 1, eventually we got to 2, eventually we got to 3. They're not growing quickly, but they are growing. So this means that as the square root of n continues to grow larger, as n approaches infinity, this means that the limit as n approaches infinity of the square root of n is equal to, now of course remember we talked about powers. This can be thought of as n to the 1/2 power, and we can take a power out and take a power of the entire thing, which would mean that this is equivalent to the square root of the limit as n approaches infinity for n. So this, we just said, is going to be equal to infinity. So in this case, this is divergent. In the next example, we're going to find the limit as n approaches infinity, and we're going to have 1 plus 2 to the n squared divided by 5 plus 3n plus 4n squared. Now, looking at this term, this might look a little bit difficult. So what we're going to do is we're actually going to use a trick where we are going to divide by the highest power in the denominator. So we're going to divide everything by n squared. So if we did this, this becomes the limit as n approaches infinity, 1 over n squared plus 2n squared divided by n squared divided by 5 over n squared plus 3n over n squared plus 4n squared divided by n squared. And this will mean that, for first of all, these two n squares will cancel. This n square will just be left over as it cancels with this n. This n squared will cancel. So now we're going to be left with is the limit as n approaches infinity, 1 over n squared plus 2 divided by 5 over n squared plus 3 over n. And now, if we were to consider the fact that this is just 1 over n squared plus 2, what we can do is, remember, with our rules of limits, we can take the limit of the top terms and the limits of the bottom terms, and then the limit of this plus the limit of this. This is going to be equal to the limit as n approaches infinity for 1 over n squared plus the limit as n approaches infinity for 2 divided by the limit as n approaches infinity, 5 over n squared, plus the limit as n approaches infinity, 3 over n. Which, remember, based on our rules we could actually pull this 3 out, because it's the same thing as saying 3 times 1 over n. So I can change this to 3 times 1 over n. Similarly, this can become 5 times 1 over n. So now, if we take the limit as n approaches infinity, 1 over n squared, what's going to happen to this term? This term is going to go to 0. If we take the limit of 2, we talked about the fact that a limit of a constant is the constant. So this is going to be equal to 2. If we take the limit of 1 over n squared as n goes to infinity, this also will go to 0. 0 times 5 is 0. And then same thing, if we take the limit as n goes to infinity, 1 over n, this will go to 0, and 0 times 3 will also be 0. So then we're left with, oh, I forgot my 4. Sorry. So when we take the limit of this 4 also, we're left with 2 over 4. For the next example, let's take the limit as n approaches infinity for 2 to the nth power minus 1 over 6 to the nth power. And we'll see if this exists, whether it converges or diverges, and if it does have a limit, what does it approach? So the first thing I'm going to do is whenever I have a fraction of two terms divided by a single term, I can actually split this up. So this is going to be the limit as n approaches infinity, 2 to the nth over 6n minus, so what I'm doing is I'm taking the limit of the top and the bottom, or taking the limit of the whole thing, I'm splitting this into 2n over 6 to the nth, minus 1 over 6 to the nth. And then what I'm going to do is I'm going to take the limit of both of these terms individually. So remember, the limit of a plus b or a minus b became the limit of a plus b, limit of b, or the limit of a minus limit of b. So in this case, this would be the limit of 2 to the n over 6 to the n minus the limit as n approaches infinity, 1 over 6n. Now, based on this, what we can do is we can actually convert this 2 to the n over 6 to the n. Remember those exponent rules? Well, in this case, this is going to be the limit as n approaches infinity, 2 over 6 to the nth power, minus limit as n approaches infinity, 1 over 6 to the nth power. Okay, so now that we have both of these in terms of its nth power, because this one could also be considered 1 over 6 to the nth power, because 1 to the nth power still be 1. Now that both of these have this power, what's going to happen with this? Well, it's going to end up being a fraction going up to a power that's getting bigger and bigger. Remember, we talked about that with our geometric sequences. If we had that r was between 0 and 1, then our r to the n was equal to 0. So in this case, this is going to go to 0. This is also going to go to 0 as we take our limit as n goes to infinity for both terms. So this is going to end up being 0 minus 0, which means that it converges to 0. For this next example, if you look at my notes here, we have two different ones. We have a to n equals n squared divided by 2n plus 3n squared, and bn equals 3 minus 2/3 n, or plus negative 2 over 3 to the nth power. So the first part, if you look at these notes, what this is saying is one approach you could take is a more numerical approach to this, where you actually just start plugging in your values of n. N equals 1, n equals 2, n equals 3, n equals 4, and see if a pattern starts to emerge. So you can see an example here, which I'm not going to write down all these numbers, but if you look at the first one, an, it starts with 0.2, then 0.25, then 0.2727, then 0.2857, then 0.2941. And if you were to continue on with this, you would see that it seems to be approaching kind of around 0.4, right? Or somewhere in the 0.3 to 0.4 range. Looking at Bn, we have 2.33333, 3.4444, and notice that with this one, it's kind of alternating a little bit. It's going, starting at 2.33, going up to 3.44, going down to 2.77, or 2.70, and it's kind of going up and down. It's oscillating, but it's getting smaller. The jumps are getting smaller each time it does this. So in this case, it looks like it's actually going to be converging on something. So now what we're going to do is we're going to do both of these analytically to see what we get. So if we were to take the limit as n approaches infinity of our an, which was n squared divided by 2n plus 3n squared, and we have our second one is the limit as n approaches infinity for bn, which was 3 plus minus 2 over 3 to the nth power. So for this first one, I'm going to use that trick we talked about earlier. I have an n squared in the denominator. I'm going to divide everything by n squared. So this is going to be the limit as n approaches infinity, n squared over n squared, divided by 2n over n squared, plus 3n squared divided by n squared. So these n squares will cancel, leave me with 1. This n will cancel with one of these n's, and these n squares will cancel. This is going to leave me with the limit as n approaches infinity, 1 over 2 over n plus 3. And now, if I were to actually apply this limit, what's going to happen to these terms? Well, if I wanted to be specific about it, what I'm looking at is this. Is I'm going to take the limit of 1 divided by the limit of 2 over n plus 3, which then I can split into the limit of 1 divided by the limit of 2 over n plus the limit, and all of these are as n goes to infinity. I'm just doing this to kind of go a little quicker, of 3. Well, the limit of a constant is that constant, so this equals 1. The limit as n approaches infinity, 2 over n, so as the bottom term, the denominator, gets bigger, this whole term is going to go to 0, plus, and then we have the limit of 3, a constant. So then this gives us 1 over 3. So what our first sequence was actually converging to was 1/3, or 0.33333 repeating. Now let's look at the second one. Limit as n approaches infinity, 3 plus minus 2/3 to the nth power. So first thing I'm going to do with this one is I'm going to split it just like we did before using our rules of limits. So I'm going to take the limit as n approaches infinity of 3 plus the limit as n approaches infinity minus 2/3 to the nth power. Now, this first term, because it's a constant, this is just going to be equal to 3. So this one we don't have to worry about. What we do have to consider now is this second term. For the second term, what I'm actually going to do is I'm going to do a trick where I'm going to split this into 2 terms. This is the same as saying -1 times 2/3. So this would be the limit as n approaches infinity, -1, times the limit as n approaches infinity, 2/3. And then both of these are to the nth power. So what's happening with this term as we take the limit as n approaches infinity? Well, it's going back and forth between -1 and +1, right? So nothing's really happening there. This term, if we look at it, this is a fraction, which is, again, between 0 and 1. So as n gets bigger, this power, right, we talked about this, we have r to the n. If r is between 0 and 1, then it's going to go to 0. 0 times anything else is going to be equal to 0. This is just going to leave us with 3. For our next example, we're going to look at whether the sequence an equals 2n squared plus n minus 1 divided by n squared converges or diverges. So we're going to do this, of course, by taking the limit of this sequence. So we're going to take the limit as n approaches infinity of 2n squared plus n minus 1 divided by n squared. So for this one, you could try dividing by n squared, but what's going to happen is you're going to end up with 2 plus 1 over n minus 1 over n squared divided by 1. You're still going to end up with that n squared denominator. You definitely can do that, and it would work. But what I'm going to do in this case is I'm just going to split this fraction. So this is going to end up being the limit as n approaches infinity, 2n squared over n squared plus n over n squared minus 1 over n squared. And it's going to give me the exact same value, because that's really all we're doing, is we're just splitting the fraction when we do that. So these n squares are going to cancel. This n is going to cancel with this n square, and we're going to be left with the limit as n approaches infinity, 2 plus 1 over n minus 1 over n squared. Now, using our rules of limits, I can split this into the limit of 2 plus the limit of 1 over n minus the limit of 1 over n squared. So this is going to be, again, I'm going to shorthand. I'm going to leave off the n goes to infinity, but they all do. So limit of 2 plus the limit of 1 over n minus the limit of 1 over n squared. And now we can look at these terms individually. Well, the limit of a constant is a constant, so this is going to be equal to 2 plus the limit as n goes to infinity, right, because these are all as n goes to infinity. And this term, 1 over n, this is going to go to 0. This one is also going to go to 0, and we're going to be left with 2. What about this sequence? Bn equals n squared divided by the square root of n cubed plus 4n. Okay, so now for this one, we're taking the limit of this. What I would want to do first is actually get everything either out of the square root or under the square root. So what we're going to do is we're going to take the limit as n approaches infinity, And I'm just going to jump straight to that step. So what I'm going to do is I'm going to put the entire thing under the square root. Now, if I wanted to make this a square root, I would have to consider what would cause it to be n squared, and this would be n to the fourth power, right? If I took the square root of n to the fourth, this would give me n squared. So this would be over n cubed plus 4n, and I'm taking the square root of this entire thing. Now, you might wonder why I'm doing this. Well, I'm doing this because then I can use one of those rules we talked about, where the square root of whatever's inside, I can take the square root of the entire thing. Because remember, anytime you see this is kind of the same thing as saying n over 4, n cubed plus 4n to the 1/2 power. In which case, what can we do with that? We can take the 1/2 power of the entire thing. So this is going to be the limit n over 4 over n cubed plus 4n, and then we take the square root of the entire thing. So now what I'm going to do within the square root is I'm going to do our trick we did previously. I'm going to divide by the largest power in the denominator. So this is going to be the square root of the limit as n approaches infinity, n to the fourth power over n cubed, divided by n cubed divided by n cubed, plus 4n over n cubed. So this n cubed is going to cancel with 3 of these n's. These are going to cancel, leave me with 1. This 1n is going to make this squared. So this is going to leave us with the square root of the limit as n approaches infinity, n divided by 1 plus 4 over n squared. Now, what we can do with this is I can actually split this into the different parts, right? Because I can take the limit of the top divided by the limit of the bottom. And then this limit of the bottom I can take as the limit of 1 plus the limit of 4 over n squared. So this is going to be the limit as n approaches infinity, n, divided by the limit as n approaches infinity, 1, plus the limit as n approaches infinity, 4 over n squared. And now I can actually evaluate each of these terms individually. What happens with the limit of n as n goes to infinity? It approaches infinity. So this is going towards infinity. What happens with the limit of a constant? Well, this term is going to be just the constant. So this is going to be 1. 4 over n squared. As n gets bigger and bigger towards infinity, this whole term is going to go to 0. So I'm going to be left with a term that is approaching infinity over 1 under the square root, which means that basically this is equivalent to saying infinity, so it diverges. For our next example, we're going to be taking the limit of this sequence, Cn equals 3 plus 5n divided by 2 plus 7n. So first thing we're going to do, we'll set up our limits. We have the limit as n approaches infinity, 3 plus 5n divided by 2 plus 7n. So what I'm going to do is just like before, I'm going to divide by the highest power of our n in the denominator. So in this case, it's just n to the 1. So this is going to be the limit as n approaches infinity, 3 over n plus 5n over n divided by 2 over n plus 7n over n. These n's will cancel, so we'll be left with the limit as n approaches infinity, 3 over n plus 5 divided by 2 over n plus 7. So as before, what we can do is we can take the limit of the top over the limit of the bottom. This limit of the top can be split into the limit of 3 over n plus the limit of 5. This bottom can be split into the limit of 2 over n plus the limit of 7. So we can actually kind of just evaluate them individually. So for this first term, when I take the limit as n goes to infinity, what happens when you have the denominator is approaching infinity? The whole fraction is getting smaller and smaller and smaller until it becomes a 0. It's approaching 0. The limit of a constant is just going to stay that constant. Again, limit of 2 over n is getting bigger, so the whole fraction is getting smaller, it's approaching 0. And then the limit of a constant is a constant. We are left with 5 over 7. What about if we had something like this? What about if we had a sequence dn which would be the cosine of n pi over 2. Well, with something like this, if we were to take the limit of this sequence, so limit as n approaches infinity, cosine n pi over 2. What's going to happen as our n is increasing? Well, if you look at what cosine does, cosine basically just looks like this. It goes from 1 to -1, and then it's going to keep repeating the cycle. So in this case, this means that it's never going to converge because there's nothing causing it to shrink or narrow down to a specific term. So in this case, this one does not exist. This would just be a cycle that continues back and forth from -1 to +1. And that's going to be it for this lesson. When we come back, we're going to keep building up the building blocks we're going to need before we actually start getting into the main topic of this course, which is going to be, of course, derivatives. But limits are really our foundational thing that we need to understand in order to build up to doing that. So this is why it's kind of important that we understand what happens with these functions and sequences and series as we take some limit. In this case, we're taking a limit as n goes to infinity, and then we'll look at what about if we have limits that go to a particular point. So there's lots that we're going to be covering in this course. I know it was kind of jumping around in the beginning as we looked at a lot of review, and this one we're kind of just speeding through, and it's because I'm just trying to build some of the basic foundational stuff that hopefully have been covered elsewhere, and then we can actually jump into building up new skills with calculus. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.